Hello, and welcome to Zaption Tour 6.1, Solving Systems by Graphing. There are 6 boxes. The first box, I want to talk to you about some definitions. So the thing that we're going to be working with this particular tour is systems of linear equations. And what we need to understand is that a system of linear equations is nothing more than when you solve 2 or more linear equations at the same time. That's really all it is, just solving 2 or more linear equations at the same time. So let me give you an example of what I mean by 2 systems. This could be a system right here. I could give you y is equal to x plus 2. That's just a line. It's a linear equation. No big deal. That's one of them. But the definition says that we need 2 or more. So then I have to write another one. So let me give you another one. Y equals, how about 3x minus 2? So this right here, solving 2 or more together, this is what's called as a system. It's when we solve 2 or more equations at the same time together. The next part of the definition that I want to talk to you about is any ordered pair that make all of the equations in the system true is what's known as a solution of the system of linear equations. So the idea here is to talk about what does it mean to be a solution to the system. So let me show you an example of this over in Fluid Math. So here is that same system that I had before at the very top. Y equals x plus 2 and y equals 3x minus 2. And what I'm going to do is I'm going to graph both of these at the same time for you. Okay? So here they are. Here's the graph. Let me bring it over here. All right. And let me zoom in just a little bit more. And even just a little bit more from there. Okay. So from this particular graph, what can we see? Well, we can see that these two graphs, or these two lines, intersect at one point. And the point that they intersect at looks to me like 2, 4. So let me write the ordered pair down, 2, 4, and graph that as well. And it's a little tiny green dot, which you can see right there. So let me bring this over to our notes so that you understand what I'm talking about here. And there it is right there. So for this particular box, it says any ordered pair. So the ordered pair that we're talking about would be the ordered pair 2, 4. This is an ordered pair. It's an x, y coordinate point, and it makes both of the equations true. Remember that my system was this. It was y equals x plus 2, and then the other one was y equals 3x minus 2. So the way that we could check to make sure that this is right is plug it in. This is our x, this is our y. So does 4 equal 2 plus 2? Yep, 4 equals 4. That means that this is true or it works for this linear equation. Plug in the same point. So 4 equals 3 times 2 minus 2. Does 4 equal 6 minus 2? It sure does. 4 equals 4. So that's also true for this linear equation. So since the ordered pair 2, 4 is true for both of these together at the same time, it is considered a solution. Box number 2 is an example. It says, what is the solution of the following system? So I have y equals 2x plus 4 and y equals x plus 2. So what we want to do is I want to show you the graphs of these. So here we go. Y equals 2x plus 4 and y equals x plus 2. So let's graph both of them simultaneously at the same time. So graphing both of them at the same time and zooming in, I'm looking for where they intersect. I'm looking for where the ordered pair that makes both of them true. I definitely see an intersection point which looks to me like the point -2, 0. Looks like -2, 0 is the intersection point. So I'm going to take that information and I'm going to bring it back over to our graph or to our notes here. And there you go. And then if I want to check to make sure that this is indeed true, I would run this point through each of my linear equations and see. Remember, this is my x, this is my y. So does 0 equal 2 times -2 plus 4? Does 0 equal -4 plus 4? Yeah, it sure does. 0 equals 0. So that makes it true for my first equation. check the second equation. Is it true that 0 is equal to negative 2 plus 2? Does 0 equal 0? Yes, that's also true for the second equation. So since the ordered pair is true for both equations, it must be a solution. Box number 3 is a U-try. What is the solution of the system of equations represented by the graph below? The solution is the ordered pair 6, 3, because it's where the graphs intersect. Box number 4 is writing a system of equations. It says that scientists studied the weight of 2 alligators over a period of 12 months. The initial weight and growth rate for each alligator is shown below. After how many months did the alligators weigh the same amount? All right, so what we need to do is we need to relate, define, and then write. So here are the steps that we're going to take. The first thing that we want to do is relate. We want to relate the information that we have. Okay, so what do we know? Well, we know that the alligator weight, which I'll just call W for now, the alligator weight is equal to the initial amount that it starts with, it was born at, so the initial amount plus the growth rate, whatever that happens to be, multiplied by however long that this alligator has been alive, so we'll just call that T for time in months. So it's important to do this step first just to talk it out. The weight of the alligator has to be, well, however much it started off as being born with, plus the growth rate times every single month that we have. That's the first thing we want to do. The next thing that you want to do is you want to define some variables, okay? I kind of already did that first to begin with, right? So we're going to say let W equal the weight of the alligator. And we're going to let T equal time. And the time that we're doing here is in months. And the weight of the alligator is measured in pounds. So we want to make sure we have that. All right, so last thing we want to do is we want to write the equations. We want to write the equation. All right, so I have 2 different alligators here. I have alligator number 1, and I have alligator number 2. So I've got 2 different alligators. Okay, alligator number 1. Let's do that one first. I'll do this one in orange for you. The weight of this alligator is going to be equal to his initial weight, which was 4 pounds, plus the growth rate is 1.5 pounds per month. So 1.5 pounds for every month T. That is the weight. That's my equation for alligator number 1. In red here, I'll do this one, alligator number 2. His weight is equal to 6 pounds plus a growth rate of 1 pound for every month that he is alive. So now I have what's known as a system of linear equations because I have solving 2 equations at the same time. Now the question says, after how many months did the alligators weigh the same amount? Well, I have something set up here for you. So here we go. So I plugged in the 2 equations already. So I have 4 plus 1.5x, and I have 6 plus x. You can see that in Desmos, I'm comparing time in months to weight in pounds, and I have an ordered pair 4, 10. We interpret that at after 4 months, both alligators weigh 10 pounds. So that's how we would answer the question. So we would say after 10 months, the alligators both weigh, or excuse me, after 4 months, rather, the alligators weigh 10 pounds. So after 4 months, the alligators weigh 10 pounds. Box number 5 is a graph of how to organize and classify systems. So I'm going to pause the video and I want you to copy down this chart before we move on. Okay, here we go. How to classify a system. Well, to begin with, if we start here of our journey, okay, our system can either have a solution or it could not have a solution. So let's go this route first, okay? If it has a solution, then the word that we use to describe it is consistent. Okay? The word that we use to describe it is consistent if it has a solution. Now, there are 2 different words that we can use to describe consistent. It can either be independent or it can be dependent. So up here, independent or it could be dependent. Okay, so again, if a system has a solution, the word that we say is consistent. If it's consistent, it can be either independent or dependent. The independent graph looks like this. Okay, it is a spot where the graphs meet exactly one time. The word for dependent looks like this, or the graph for dependent looks like this. It is when two equations represent the same line. Okay, so here you can clearly see that there is only one solution. And that one solution is the ordered pair point. In this graph, you can see that there are infinitely many solutions. That's because the two lines represent the same equation, and I'll show you an example of that in a second. Okay, the other direction we could go, the complete other direction, is this. If your system has no solution, the word that we use to describe it is inconsistent. All right? And if it's inconsistent, then its graph will look like this. It will be two parallel lines. The reason there'd be parallel lines here is because there is no point of intersection. The blue line will never cross the red line, therefore there is no common point. So again, here's the way that we classify systems. It either has a solution or it doesn't. If it does have a solution, it's consistent, and it could either be independent or dependent. If you have an independent system, then you have exactly one solution, and the graph will look something like this. If you have a dependent system, that means you have infinitely many solutions, and it's basically one line on top of the other. If your system it has no solution, we call it an inconsistent system, and you're going to have graph of the lines will be parallel. Okay, I'm going to ask you three questions, A, B, and C. How would you classify the following systems? What words would you use?